All right, guys. What have we done so far? We've done solutions, we've done solubility, we've done concentration, and now we're going to do colligative properties, which is basically why we throw so much salt on the highways on like a regular basis. We're going to figure out why. Get your pencil, get your paper, giddy up, let's go. So what are colligative properties? What is this silly word that I'm saying? Basically, colligative properties are the effects that a solute has on the physical properties of a solvent. So what that means is, like, when you dissolve, let's just use water. When you dissolve stuff in water, you change the physical properties of water. It's true. Let's look at one property, which is like viscosity, or like how thick it is, right? So if you take pure water and you pour it out of a cup, it just, it pours out like it's, like water. However, if you dissolve a lot of sugar, like a lot of sugar, so much so that it starts to turning into like, mapley, syrupy type stuff, if you try to pour that out, it'll be much more thicker, right? That means it has more viscosity. So that's like a physical property, you know what I mean? But the two physical properties that we are going to be talking about today are boiling point and freezing point. Yeah, there's that. So again, colligative properties are the effect that a solute has on the physical properties of a solvent. And there are a couple of really trippy things like going on with this. One thing that's really weird. So one thing that's really weird is that, like, it actually doesn't even matter what it is. Like, it doesn't matter at all, which doesn't make any sense, but, there it is. The only thing that matters, like, the only thing that actually has the effect, the thing that creates the effect, is the number of dissolved particles. So it doesn't matter what you dissolve. So the solute itself doesn't really matter. The only thing that matters is how much of that solute you can dissolve into the water. That's it. So the identity of the solute matters not, completely doesn't matter at all. The solute is like the physical properties of the solute. Like, once you dissolve it, like, that's it. That's kind of where it stays. Nothing really changes about the solute. Fun fact, like, we use salt, right, on the roads. I don't know if you've ever seen that before, but like over in Vermont, where they make a lot of cheese, there's this stuff called whey, which is like the water that's left after the cheese curds are kind of scooped off. Well, it's full of dissolved stuff, and what they were doing with this whey is they would take it out and just dump it into the ditch, or out on the like hayfield or something. They just got rid of it, which was kind of a shame. In comes winter. They're dumping lots of salt on the roads. Salt is, one, pretty expensive, and two, it is destroying the environment ever so slowly, because we have freshwater animals and plants and things in our rivers and streams, and once we have an entire winter's worth of salt washing off into those freshwater streams and stuff, we're actually affecting the salinity of our freshwater streams and whatnot. Very bad if you're like a little fishy trying to be alive in freshwater if there's a lot of salt. So they use this whey. They put it in a truck and they sprayed it on the road, and it worked just as well or better than like laying salt on the road. So truly, it can be anything. Man, if you're in Vermont, maybe you can even like throw some maple syrup on the road, but that would be a waste. But truly, it really doesn't matter what you put in. Like, it doesn't matter what you put into the solvent, as long as it dissolves and makes dissolved particles. That's it. So here's the thing, changes in boiling point. So I like to think of it this way: as boiling point is hot, it just gets hotter. Okay, so 1 mole of dissolved particles, right? So you guys know what a mole is. If you can dissolve 1 mole into 100 grams of water, this is equal to 1 liter. You can raise the temperature of boiling by 1/2 of a degree centigrade. So 0.52 Celsius, that's like, it's about, oh man, I hate that. 0.52, what is that? It's about 0.9 degrees Fahrenheit. So it's about 1 degree. So the 1 mole of dissolved particles increases the boiling point by 1/2 a degree centigrade, which just to like make it relevant, about 1 degree Fahrenheit. So what that means is, the more stuff you dissolve in the water, the hotter the boiling point is going to be. And man, this is what mapling is all about. This is what sugaring is all about. If you talk to folks that sugar, you like take the maple sap and you boil it, and you boil it and boil it and boil it and boil it until it gets to a certain temperature, right? And it's that temperature is where they say, okay, we're gonna that's when it's maple syrup. Because by boiling off the water, right, you're like reducing the amount of solvent, so the concentration goes up and up and up. The concentration of sugar and all the other stuff that makes maple syrup so beautifully, amazingly delicious. So as that concentration increases, the boiling point increases. You guys get what I'm saying? So that's how like sugar shacks measure or are able to tell when maple sap has turned into maple sugar. It's when the boiling point rises, right? Because as the boiling point rises, that's how they're measuring the concentration of sugar and stuff. That's wonderful. You dig? Awesome. So that's what happens to the boiling point. The boiling point that is hot just gets hotter by about 0.5 degrees Celsius for every mole of dissolved particles. Now, freezing point is cold, so it just gets colder. So again, 1 mole of dissolved particles drops it by 1.86, which was about, what did I figured out to be about 3.4 degrees Fahrenheit. So yeah, again, 1 mole of dissolved particles lowers the freezing point by 1.86 degrees Celsius. In other words, it has to get colder in order to freeze. This is why we put salt on the road. We put salt on the road because as soon as the salt and the water hit, it just starts dissolving, and those dissolved particles make it harder for the water molecules to kind of connect and get together to freeze, so it has to get even colder than 0 degrees centigrade, which is great because it melts the ice. Unless it gets too cold, then, the only thing you can do is throw some sand on the road. But, yeah, so more dissolved stuff, the cold freezing point gets even colder. Got it? Great. This is a picture because I can't remember anything. So increasing the boiling point, 0.5 per mole and 1.86 per mole. So this is like the picture I draw. Anytime I have these colligative property, what happens with like your concentration, boiling point, freezing point, I draw an arrow that goes from left to right. You dig? And this is like more dissolved particles, which means more concentration. You guys get what I'm saying? So more concentration, what happens to the boiling point? Well, it goes up, right? So the boiling point, which is already hot, gets even hotter, and the freezing point that is cold gets even colder. And the numbers we have to remember are 1.5 and 1.86. Got it? Wonderful. Like I said, that picture right there, that is what I draw so my brain can remember, because the questions will be like, what happens when you dissolve more? What happens when you dissolve less? So if it's less, you start here. Like if you decrease the concentration, you go that way. And what happens to boiling point? Well, as I'm going this way, it drops, right? What happens to freezing point? As I'm going this way, it increases. You see? However, if I'm going more concentrated from less concentrated to more concentrated this way, boiling point goes up, freezing point goes down. You guys get what I'm saying? Lovely, I'm sure you do. All right, so there's a bit of a thing here, because not all solutes act the same or are as good at being colligative and whatnot. So here's the thing, molecular things. If you remember, molecular, that word, anytime you see that word, it instant means covalently bonded. And anytime you see something that is covalently bonded, there is one element that you need to be aware of, and that is carbon. Got it? If it's like a carbon-based thing, it's going to be molecular. So here's the thing with things that are molecular. They don't break apart when they get dissolved. They all stay together. The reason why molecular things dissolve is because they have polar bits and pieces, but the molecule itself will not break apart. So what that means for us, like in terms of like colligative properties and whatnot, is that if you have 1 mole of a molecular substance to start with, when you dissolve it, you will have 1 mole of dissolved particles. And if you look, you see how this starts with carbon? Yeah, molecular, covalently bonded. It does not break apart. So anything carbon-based will not break apart. 1 mole yields 1 mole straightforward. Easy peasy lemon squeezy. right? Okay, now for the next part that's going to be a little more complicated, and that's going to be our friends, the ionic stuff. Now, the ionic stuff, now these are ionic particles that are all stuck together by their like electrostatic attraction of the positive charge and the negative charge. And what happens is when they get dissolved, they are literally ripped apart. All the ions are separated and evenly dispersed throughout. So what that means is 1 mole of dissolved ionic substance will yield more than 1 mole of dissolved particles. Now, how many more moles? Depends on the stuff. Got it? So let's start with the easy stuff. Sodium chloride. Everybody knows this. This is like table salt, right? But if we look at sodium chloride, it is made out of 2 ions. It has a sodium ion and it has a chloride ion. 2 things, 2 ions, right? So when we put this into water and we dissolve it, we get not just 1, but 2 different dissolved particles. Does that make sense? I certainly hope so. Now let's look at calcium chloride. If we look at calcium chloride, we start with 1 particle of calcium chloride, but how many are there here, right? If we look at the chemical formula, we've got 1 calcium and how many? Oh yeah, not 1, but 2 chlorines. You guys see that? So 1 calcium chloride yields 3 total particles. So it's like a triple whammy. You guys get what I'm saying? So this is why we use some slightly different salts. That's why you don't want to put rock salt like on your potato chips, because it is not. It's salt, but it is not table salt. Got it? Awesome. Now, when these ionic substances break apart, right, they're going to yield more particles. So what you need to be able to do is count how many particles each ionic substance is going to make. All right, so this one, KBr. Let me go to good color. We just did purple. What color should I use? How about this green color? All right, KBr. If we look at this, we have 1 potassium, we have 1 bromine, so this will make 2 particles when we dissolve it in water. Nice. Now let's go to the other one. Remember before when we were like counting number of atoms and stuff for like the chemical formulas and whatnot? Same thing. So how many magnesiums do we have? Oh, 1 magnesium. I'm looking over here. Okay, so here's the thing. Remember, polyatomic ions. This NO3 is a polyatomic ion. How do I know? Well, the brackets give it away. Also, there's like 1, 2, 3 capital letters, so there's gonna have to be a polyatomic ion. Go to table E and figure it out which one. Remember, polyatomic ions, you need to recognize it and look it up. So this one you don't even need to like look it up though. You just need to recognize that this is your polyatomic ion. It acts like 1 ion, right? It's polyatomic ion. 1 ion, many atoms, right? So how many are there? Well, here's your little subscript, and that subscript is right next to your parentheses, so that tells you that there are 2 of that particular polyatomic ion, giving us a grand total of 3 particles for magnesium nitrate. Next is NaOH. Well, I've got 1, 2, 3 capital letters. I guarantee you there's a polyatomic ion in there. And if I go to my reference table and I look it up, there you go. All right, here is my polyatomic ion right here. Right, so I don't see any parentheses. I don't see anything at all. So there's just one of those. So I've got 1 sodium. I've got 1 hydroxide. I've got a grand total of 2 particles. Again, why do I care? Because this is going to tell us like the degree of colligative effects that this substance can have, right? Because that's good to know. All right, H3PO4. I see not 1, not 2, but 3 capital letters. You're right, polyatomic ion. Let me look it up right quick on my reference tables here to see which polyatomic ion I have. And sure enough, the PO4 is a polyatomic ion. So let's see here. I've got 3 hydrogens, no parentheses or anything. So that's just 1 PO4. So that will give me 4. Wow, 4. So which one of these substances would have the greatest colligative effect? This one right here. Because it will make 4 particles when you dissolve it in water. Delightful. All right, so question is, what will the boiling point and freezing point of H2O be if we added 1 mole of the following to 100 grams of water first we got to get a couple of things lined up. Freezing point. What happens to the freezing point? Well, the freezing point, if I get it right, the freezing point is going to drop by 1.86. And the boiling point is going to increase by 0.52 degrees. All right, so that I just got to like keep that clear in my brain. And the next thing I got to do is figure out how many particles it is, and then we'll find our new boiling point and freezing point. So let's start with this first one. And look, man, I'm seeing you right here. See this first one? See that? Carbon. So we know that if you have carbon, it is only going to make one dissolved particle. You get it? Awesome. So if you start with 1 mole of this substance, you can only make 1 mole of dissolved particles because it doesn't break apart. Like, yeah, it just stays put. So what happens to the new freezing point? Well, let's remember that the freezing point starts at 0, right? So if it's going to drop by 1.86, the new freezing point will be negative 1.86 because we have 1 mole of dissolved product. Now the boiling point, if I get my face out of the way here for a minute, the boiling point will increase, and it's going to increase by 0.52. So it starts out at 100, and it's going to jump up by about a half. So now this one will be 100.52 degrees centigrade. You guys picking up what I'm putting down there? Lovely. Let's try number next. The next one is NaCl. Now for this one, you remember we already did this before. We have 1 sodium, we have 1 chlorine, so this makes 2 particles for every mole. Awesome. So if we start with 1 mole, we will actually get 2 moles of dissolved particles, right? So what that means is the freezing point is going to drop 2 times 1.86 because there are 2 moles. So let's get out our new handy dandy thingamajig. And so it's just 1.86 times 2. That gives me negative 3.72. So it's going to drop 1.86 and then drop 1.86 again. So it would be negative 3.72. Now, our boiling point, on the other hand, it's going to get warmer. Not once, but twice. So it's going to go up 0.52, then up 0.52 again, leaving me with a final boiling point of 101.04 degrees centigrade, of course. And now the next, ooh, I see it there too. See that? Carbon. Dude, if it is carbon based, is it going to break apart? Is it going to break apart? Nah, it's not going to happen, right? So this is only ever going to make 1 particle. It will not break apart. So if we start with 1 mole of this stuff, you will only have 1 mole of dissolved particles. And look, I'm going to cheat here a little bit. See this? Y'all see that? Same exact number of dissolved particles. And if you remember, it doesn't matter what the substance is, it only matters the number of dissolved particles. So if I have 1 mole of dissolved particles, I like the freezing point, negative 1.86, that's it. Boiling point, 100.52, it's exactly the same. We get the exact same results regardless of what the substance is. That's why colligative properties are a little bit weird. All right, so let's do this next one here. Sodium chloride. Here we have 1 sodium, and don't forget, this is our polyatomic ion called hydroxide, and there's only 1 of them there. So when we dissolve sodium hydroxide, it will make 2 particles, right? So if I have 1 mole of sodium hydroxide, I will end up with 2 moles of dissolved particles, and look what we have here. Right? So the freezing point and melting point exactly the same because you have the exact same number of dissolved particles. So my freezing point is going to be negative 3.72, and my new boiling point is going to be 101.04. Lovely. That just lovely, that one. All right. Let's go on to this one. So let's see how many particles we're going to make. We got 1 calcium. Remember, this is our polyatomic ion. And oh, yeah, I see there are 2 of them. So this ionic substance will make 3 moles when we dissolve it in water. So if we start with 1 mole and we dissolve it, 1 mole of calcium nitrate will create 3 moles of dissolved particles. So what's my freezing point? Easy. We're going to take 1.86 and we're going to multiply it by 3. And we're going to get 5.58. right? How do we calculate the new boiling point? Well, we take 3 and we multiply it by 0.52. And that's how we do that, you dig? Awesome. All right, one thing before we get any further, I want to look at how it can get a little bit more ugly. Like this one, let's start with calcium nitrate. Let's say instead of 1 mole, let's do 3.9 moles. Right? So calcium nitrate will make 3 particles for every mole. So each calcium nitrate makes 3 moles. If you have 3.9 moles, how many particles do you have in all? Well, you're going to take the number of particles, and you're going to multiply it by the number of moles, and you're going to get 11.7 moles of dissolved particles, right? Because 1 mole makes 3, 3.9 makes 11.7. You dig? All right, so what is our new freezing point? Well, I can't do that math on my own, so I'm going to take the number of moles of dissolved particles, which is 11.7, and I'm going to multiply that by 1.86. Wow, that's going to be really cold. That will be minus 21.762 for my new freezing point. Now, how do I find the boiling point? Same thing, only multiplied by 0.52. So I'm going to take the number of dissolved particles, which is 11.7, and I'm going to multiply it by 0.52, and I will have a new boiling point of 106.084. Got it! You got it! I know you got it. Bam! Done. End. Understanding colligative properties is how we're going to practice all this loveliness. Yeah, hope you guys have an awesome day. I'm having like a kind of a super awesome day myself, and I will see you next time I'm looking at you.